Before I start with the law number 0, there's one concept I have to discuss a little bit, and that's the concept of equilibrium. What we've used so far is the requirement that if we have macroscopic data available about a system, then we assigned to that system that state which, under given constraints in the form of these macroscopic data, maximizes the entropy. That was a statistical argument or an information theoretic argument based on the idea that the macroscopic data constitutes all the information that we have about the system, and then we should assign to the system a state that contains the given information only and nothing else. No further spurious information that's not contained in the macroscopic data that is given to us. That was the idea of assigning maximum entropy states on the basis of macroscopic data. What we have not yet discussed explicitly, we've used it implicitly in various places, but we haven't discussed it explicitly yet, is what kind of observables are these that are given to us, either as sharp constraints or as expectation values. There are a handful of observables that we've used all over and over again. The energy, the particle number, sometimes the magnetization. And why is it that these observables occur so often and play such a prominent role? The fact that, for example, the energy is always included in the set of observables whose values are given to us, either as a sharp constraint or as an expectation value, is the fact that the energy is a constant of the motion. And likewise, the particle number is usually a constant of the motion if the system is isolated. So these observables, when you consider an isolated system, these observables are typically constants of the motion. And this links with the definition of equilibrium. Let me start to define equilibrium of an isolated system. We're given macroscopic data, for example, energy, particle number, magnetization, things like that. We're given these macroscopic data. And under which circumstances is the system in equilibrium? When can we consider the system to be in equilibrium? These macroscopic data are sufficient to describe the macrostate of the system at the present, at this very moment, but also in the future. If the macroscopic data suffice to describe both the present and also the future macrostate of the system. And secondly, the macroscopic data won't change unless you trigger a change by exerting some external force on the system or bringing the system in contact with another system, with a heat bath, with a reservoir, with a source of heat or particles. So you have to do something to the system explicitly in order to effect a change of these macroscopic data. If, on the other hand, you let the system sit alone, undisturbed, then these macroscopic data won't change. Yeah, so when you have an isolated system and you're given macroscopic data, and these macroscopic data don't change unless you do something to the system, in that case, you can say the system is in equilibrium. So as long as you let the system alone, the macroscopic data won't change in time. this implies that the macroscopic data must relate to constants of the motion. Because if they weren't constants of the motion, then they would generally change over time. Yeah? So that's what singles out constants of the motion, that if their values are known and given at a certain time, then these values will remain the same also in the future. So the observables, AI, whose values are given as sharp constraints or as expectation values, must be constants of the motion. And this is, as I said at the beginning, this is the reason why, for example, the energy and particle number are so often singled out and part of this set of given observables, because precisely they are constants of the motion. This was about an isolated system. Now look at several systems. Look at, say, two systems that you bring in contact with each other. Say you have a system A, you have a system B, you bring them in contact with each other and you allow, for example, the exchange of energy, perhaps also the exchange of particles between the two systems. So they are weakly coupled and exchange of energy, possibly also particles, is allowed. So one also says that these two are, when the exchange of energy is allowed, one says that they are in thermal contact with each other. And now the question is, previously we talked about the equilibrium of an isolated system. Now we wonder, what does it mean to say that two systems A and B are in equilibrium with each other? Each individually is in equilibrium if you consider it as a separate system, isolated system, but now you bring them in contact and you wonder, what does it mean to say that they are in equilibrium with each other? Now the idea is to say that the two systems are in equilibrium with each other if their macroscopic properties won't change when you bring them in thermal contact with each other. So if you have a hotter body and a colder body, and you bring them in thermal contact with each other, and you allow exchange of energy in the form of heat between the bodies, then one will cool down and the other will warm up. So there will be a change of their macroscopic properties, and therefore they are not in equilibrium with each other. But if you bring them in contact and nothing happens, their macroscopic properties stay the same, then this means that they are in equilibrium with each other. Yeah? So the definition is that upon thermal contact, their macroscopic properties do not change. So you see what the two definitions have in common is, in the case of an isolated system, the macrostate will stay the same unless you trigger a change by some external force or by contact with another system. So equilibrium means the macrostate won't change, and you find the same idea here when you talk about the mutual equilibrium of two systems, A and B. Again, equilibrium means that when you bring them in contact, there will be no change of their macroscopic properties. Equilibrium means that no change will happen unless you exert some action to trigger change. Now, this lays the basis for the formulation of the Zeroth law of thermodynamics. The Zeroth law says that when two systems are in equilibrium with each other, this is equivalent to saying that both systems have the same values for all intensive thermodynamic variables. In particular, they have the same temperature. I mean, the intensive thermodynamic variables, they may include more variables beyond temperature, like pressure, chemical potential, and so on. But the temperature is always amongst them. The others, you may have additional intensive variables, but you always have a temperature, because energy is always part of the set of relevant observables that determine the macrostate, and therefore temperature is always amongst your intensive variables. So in particular, equilibrium means the same temperature. But if you have more intensive variables, then it means that those intensive variables are also equal for both systems. So in particular, you have the same temperature. Let's consider a few immediate conclusions of this statement. Now, when you say that equilibrium is characterized by identical values for the intensive variables, then this presupposes, of course, that in the first place you must have a set of intensive variables that characterize your equilibrium state. So prerequisite is that in the first place there must exist a set of intensive variables which always includes the temperature that characterizes an equilibrium state. So sometimes the zeroth law is also simply phrased as saying that there exists temperature. There exists a thermodynamic variable called temperature which characterizes equilibrium. And I phrase it here in a more general form that equilibrium means same values for all intensive variables which include the temperature, always include the temperature. And of course, this presupposes that they exist in the first place to characterize an equilibrium state. Another consequence is that thermal equilibrium between two bodies or between two macroscopic systems is an equivalence relation. It means the following: when I say two systems A and B are in equilibrium with each other, and I say that system B is in equilibrium with system C, then this implies that also system A must be in equilibrium with system C. And this is immediately evident why this must be the case, because if A is in equilibrium with B, this means that A and B must have the same values for all intensive variables. If B is in equilibrium with C, then C must also have the same values for the intensive variables as B, and therefore C has the same values for the intensive variables as A, and therefore they are in equilibrium too. So these are slightly different ways of phrasing the zeroth law. If you look in the literature, you find some of the statements that I wrote down as a formulation of the zeroth law, and there's a little bit of variation, which you say is the zeroth law and which is a consequence of that. I started with the equality of the intensive variables, and then the other statements are immediate consequences of that. Let's try to understand the origin of the zeroth law based on what we've learned so far about statistical mechanics. And I'd like to offer two arguments for the zeroth law, one on a macroscopic level and one on a microscopic level. A macroscopic argument could go as follows. And let me restrict the argument to the special case of temperature. So let me focus on the intensive variable temperature, but you can make similar arguments for other intensive variables. Let's consider two systems, A and B. The two systems are in thermal contact with each other, and separately, considered as isolated systems, separately they are in equilibrium. Let's assume the temperature does not have the same value for both systems. Let's say one of the two systems is hotter than the other. Let's assume that system A is hotter and system B is colder. So temperature of A is larger than the temperature of B. The two systems are in thermal contact, and therefore they are allowed to exchange heat. Let's say heat flows from the hotter to the colder system. So heat flows from A to B. Let me denote this amount of heat, infinitesimal amount of heat, delta Q. So an amount of heat, delta Q, flows from A to B. By the general equations that we know, delta Q is at the same time equals the change of internal energy of B. So the internal energy of B is increased by delta Q, and the internal energy of A is lowered by delta Q. So this is delta Q equals minus the change of internal energy of A, or equals the increase of internal energy of B. What do we know about the variation of internal energy? We have our general framework, which tells us that the change of internal energy, du, is given by TdS. Yeah? So for system B, this is the temperature of B times the change of entropy of system B. For system A, the change of internal energy is Ta times the change of entropy of A, and there's a minus sign in front. We can solve this equality for the change of entropy of system A, and we find this is minus temperature of B divided by temperature of A times the change of entropy of B. Now, what does this imply for the change of total entropy? The total entropy of both systems changes by dSA, that's the change of entropy of system A, plus the change of entropy of system B. Using the formula on the previous line for the change of entropy of system A, we can express that as 1 minus the ratio of temperatures times the change of entropy of system B. Now this bracket, given that B is colder than A, the ratio TB over TA is smaller than 1, and therefore in the bracket is positive. It's larger than 0. The internal energy of B increases. The temperature of B is positive, and therefore the change of entropy of system B must also be positive. Yeah, since heat flows from A to B, the entropy of B increases. This is positive. So we multiply two positive quantities, and the product must also be positive. So we find that when heat flows from the hotter system to the colder system, then the total entropy increases. This in turn implies, as soon as you have a temperature difference, then the total entropy of the system can be raised by having heat flow from the hotter to the colder. And this means that the total entropy reaches a maximum when the temperatures are equal, because then you no longer have a system that is hotter than the other, and then you no longer have the possibility to increase the entropy even further by having heat flow from the hotter to the colder. So this increase of entropy ceases as soon as you have reached equal temperatures between the two. So the conclusion is that the entropy is maximal when the temperatures are equal. At the same time, we know that an equilibrium macrostate is always described under given constraints by that state which maximizes the entropy. So when you have given constraints, the system always settles in that state which maximizes the entropy. The state which, for the combined system, which maximizes the entropy is the one in which the temperatures are equal. And therefore, equilibrium corresponds to the state in which the two temperatures are equal. So equality of temperature, therefore, is equivalent to equilibrium between A and B. This is the macroscopic argument, that you bring systems in contact, and then the total system, the combined system, settles in the maximum entropy state, and the maximum entropy state must be the state in which the temperatures are equal, because otherwise you could always have heat flow from the hotter to the colder, and in this way increase the entropy further. There's also a microscopic argument, which I would like to show you next. Assume that first the two systems A and B are not in thermal contact with each other. You consider them separately. And each system individually is in equilibrium as an isolated system. This implies, if we focus on energy and temperature here and we don't look at other macroscopic data, that both systems are initially described by canonical states. So system A is described by a canonical state with some temperature or inverse temperature beta A, with Hamiltonian HA, and system B is described by a canonical state with some other inverse temperature beta B and Hamiltonian HB. So the combined system, as long as they are not in contact with each other, the combined system is simply the tensor product of the two states. So this is proportional to e to the minus beta A HA minus beta B HB. This is before they come in thermal contact with each other. Now bring them in thermal contact. Bringing the two systems in thermal contact means allowing the two systems to interact with each other. So effectively, you switch on some weak interaction. Let me call this V. And the combined system will then be described by a total Hamiltonian for the combined system, which includes the Hamiltonians for the two systems separately, the individual Hamiltonians for the isolated systems, plus some interaction term, which you assume to be weak. A consequence is that whereas previously the individual Hamiltonians of the two subsystems, HA and HB, were constants of the motion, now that the interaction is switched on, HA and HB are no longer constants of the motion. Only the total Hamiltonian is now a constant of the motion. This in turn implies that if only you wait long enough, the system will eventually settle in a macrostate that's characterized by the value of this total Hamiltonian only. And such a macrostate, which is characterized by the expectation value of the total Hamiltonian, that will be a canonical state, a Boltzmann-Gibbs state, which now has a single Lagrange parameter only, namely beta, associated with the total Hamiltonian. So, consequence is that the combined system will eventually settle in a canonical state that is characterized by the expectation value of the total Hamiltonian only, and therefore has the form e to the minus beta times the total Hamiltonian. So there's now only a single Lagrange parameter beta. Now you can exploit the fact that the interaction is assumed to be weak. This means that to a lowest order approximation in this canonical state of the combined system, in the lowest order approximation, you can go back to expressing the total Hamiltonian simply as the sum of the subsystem Hamiltonians, and you can omit the V if the interaction is weak enough. And then you are back to a product state, just as before you brought the two systems in thermal contact, only that now you no longer have two separate Lagrange parameters beta A and beta B for the two separate systems, but you have a single Lagrange parameter beta, which is identical in both factors of this product state. How did we define thermal equilibrium between two systems? We said that when we bring the two systems in contact with each other, then their macro state won't change. Now, prior to thermal contact, the macro state was rho AB above, with this tensor product state of rho A and rho B with two separate temperatures, beta A and beta B. After thermal contact, the interaction is non-zero and therefore strong enough to eventually lead to an equilibrium state that is characterized by the total Hamiltonian only. But then on the other hand, it's weak enough so that in this final canonical state, I can then approximately write that as a product state of e to the minus beta HA and e to the minus beta HB. So the strength of the interaction is just such that it leads to equilibration, but it's weak enough so that I can factorize. Now I say this final state, which I called rho primed AB, this final macro state, this must be equal to the initial macro state. But then you can simply compare the initial macro state that was a tensor product state with two different temperatures, inverse temperatures, beta A and beta B. And the final macro state is a tensor product state with identical inverse temperature beta. And of course they can be equal only if they are all equal. So if beta A equals beta B equals beta. So in other words, if the bodies have the same temperature. Only then, bringing them in thermal contact with each other with a weak interaction won't lead to a change of macro state. The first law of thermodynamics is very straightforward. It's composed of two parts. The first statement is that the internal energy U that we have used a lot already, the internal energy U is a system property. What this means is to say that this is a property of the macro state, and regardless of how that macro state was reached, regardless of any prior history of the system. So it's a property of the macro state only, regardless of how that state was reached. Now, this is very easy to understand if you remember that the internal energy is nothing but the expectation value of the Hamiltonian in the state rho. So it's obvious that the internal energy follows directly from the state rho, is a property of the state rho. So this is obviously a property of the state rho. And it doesn't matter how you have reached that state rho. Now, the statement that the internal energy is a system property also includes the statement that U is always included in the macroscopic variables that characterize the macrostate. And we talked about that just a minute ago, that being a constant of the motion, the internal energy is always included in the set of observables that characterize equilibrium, the equilibrium macrostate. And this immediately implies the statement that U is part of the description and the property of the macrostate. So this first part of the first law says that when you want to describe a system, a macroscopic system, then you must always include the energy. This is always part of the description of the system, and it's a property of the state only and of nothing else. The second part of this law is that when you have multiple systems in contact with each other, then the total energy of all the systems, the total energy is conserved. So this expresses energy conservation. So let's say we have a system A, we have a system B, we have a system C, and so on. We have multiple systems, and you have exchanges of energy. Say there's energy flowing from A to B, from A to C, possibly from C to B, and so on. So these are energy exchanges. Then the energy of the total system is always the same, is conserved. And this is also easy to understand where this comes from, because the total Hamiltonian describing all states, all subsystems together, so the total Hamiltonian A, B, C, and so on, is a constant of the motion. This implies that the total energy is conserved. And then if you further assume, as we had done also in our argument for the Zeroth law, when you further assume that the interactions between the subsystems are weak, so they do exist, they are sufficient to allow the exchange of energy between the subsystems, but at the same time they are sufficiently weak, then you can, to a good approximation, say that the total energy is simply the sum of the individual internal energies of the subsystems, and you can neglect in this expression the energy that is caught up in interactions between the subsystems. So then you simply say that the sum of all the internal energies of all the subsystems is conserved. In fact, this property we already exploited in our arguments in favor of the Zeroth law. The third law is the only law of these four laws which is really quantum mechanical in origin, because it has to do with the ground state of the macroscopic system. It makes a statement about the ground state of the system. When you are at temperature 0, which you can never reach in practice, but you can get arbitrarily close, so you approach t equal to 0, then of course the system will be in its ground state. Now, if the ground state is non-degenerate, so there's a unique ground state, then, and only then, the system is also in a pure state. And the pure state has entropy 0. So, whenever this is the case, that the ground state is non-degenerate, then at 0 temperature, the entropy is 0. This is, however, too strong a requirement to say that in a macroscopic system, the ground state should be non-degenerate. You can relax this requirement and then make a more general statement. The degeneracy of the ground state is also called the multiplicity of the ground state. And if this multiplicity, that's the degree of degeneracy, if this multiplicity grows with the size of the system less rapidly than exponentially, so for example, by some power law, in any case, less rapidly than exponentially, then for very large systems, the ratio of entropy over volume as the temperature approaches 0 also approaches 0. Sometimes it's formulated in terms of the volume. Alternatively, you can also formulate it in terms of particle number. You can say the particle number goes to infinity, so you have a very large system. And then the ratio, so the entropy per particle, the ratio S over N, this goes to 0 as the temperature goes to 0. The way you can understand this is to say the entropy is the log of the number of compatible microstates. So here, when we talk about the ground state, the entropy as the temperature approaches 0 and the system settles in the lowest energy state, in the ground state, then the entropy is the log of the multiplicity of the ground state, up to a constant of proportionality. Now, if the multiplicity grows, say, polynomially with the size, then the multiplicity goes like volume or particle number to some power. When you calculate the entropy, you take the log of that, and the log of, say, volume to some power is proportional to the log of the volume. So entropy in this, as temperature goes to 0, entropy goes like the log of the volume. When you divide this by volume, so you have the ratio log of volume over volume, this goes to 0 as the volume goes to infinity, so when you have a very large system. Yeah. Only if the multiplicity of the ground state grows exponentially with size, then you would have multiplicity goes like e to the volume, and the log of that would be proportional to volume. And then, of course, the ratio of entropy and volume, that would be some finite number. It would not be 0. But as soon as it grows less rapidly than exponentially, then this ratio tends to 0. This is the third law. It holds true for almost all materials. So this is more an empirical statement that basically all the materials that you know and that you work with have this property that the multiplicity of their ground state grows less rapidly than exponentially, and therefore the third law holds. Let me just add one remark, that when you say you consider the limit of infinite size or very large size, then what this means is that all extensive variables tend to infinity, while their ratios are fixed. So when, for example, in the first formulation, when I say volume goes to infinity, then of course I mean that also particle number, energy, and all other extensive quantities tend to infinity. So I take this limit, size going to infinity, keeping ratios of extensive variables fixed, and hence also keeping intensive variables of the system fixed. Let me just briefly note that the limit v going to infinity, or particle number going to infinity, is to be understood, means that all extensive quantities approach infinity, keeping their ratios, for example, the number density of particles, fixed and finite. Here's a summary of all the laws that we've encountered. The zeroth law talks about the equilibrium of different systems with each other. And it says that two systems are in equilibrium with each other when all the intensive variables have the same values. And an immediate consequence of this, and sometimes an alternative statement of the second law, the zeroth law, is that equilibrium is an equivalence relation. So when A is in equilibrium with B and B with C, then A with C as well. The way we understood this was by invoking this principle of entropy maximization. We said that if this were not the case, if you had systems in contact with each other that can exchange energy or other resources like particles, and the intensive variables do not have the same value, the same values, then you can achieve an increase in entropy by shifting these resources between the systems until the intensive variables do have the same values. So this situation where the intensive variables have the same values corresponds to the situation where you have maximum entropy. Then we came to the first law, which again has two parts. One is that the internal energy is a system property, which means that it's determined by the macrostate, and it's always part of the description of the macrostate. The energy is always part of the observables whose values are given as macroscopic data. And then, secondly, the total energy is conserved. We found that this was very straightforward to understand. First of all, the internal energy is the expectation value of the Hamiltonian in the given macrostate, so it's obviously a property of the state, and it's a constant of the motion, and hence its value must be conserved. Then the second law talks about entropy. First of all, I'm not sure if I said that explicitly, but entropy, just like energy, is a system property in the sense that you can assign to any macrostate a unique entropy. The entropy depends only on the macrostate. And again, that's obvious because we have a formula for that. It's this trace rho log rho formula, and it's obviously a property of the macrostate. And when you have an arbitrary macroscopic process, then in the course of this process, the total energy can never decrease. The entropy of your final state, macro state, is always greater or equal than the entropy of the initial macro state, as long as the process or the experiment that you perform is reproducible. Well, we found that this follows from reproducibility of macroscopic experiments. And finally, the third law states that in the macroscopic limit, so for very large sizes, as the temperature approaches zero, the entropy per volume or the entropy per particle also approach zero. And this could be understood with the requirement or the observation that for most systems, the multiplicity of their ground state grows less rapidly than exponentially with the size of the system. This is on one page an overview of the basic laws of thermodynamics.